All right. So it looks like we're ready to go. Welcome to day 3 of the Algebraic Number Theory crash course, where we've probably already taken some crashes, but we're going to keep crashing. All right. So let's see. Where were we? Where have we been? So last time we quickly skipped through this norm and trace and this characteristic polynomial where we had to take my word that it's actually in the rationals. But if we think about linear transformations and determinants of matrices and Q vector spaces, it makes a little bit of sense that it might land in the rationals, and it makes sense that it'll have the things we want it to have as roots, and it makes sense that different automorphisms of K that fix Q, different ways of looking at K that fix Q are, the linear transformation is not going to care about that because it's all relative to Q. Okay, so we got norm is multiplicative. We did this computation. And then we had this example here where we destroy our, yes. That a little better? Sweet. All right, so we have here 2 examples of how to factor 6, and one can prove, as I assigned for an exercise, and I'm assuming very few people actually did, but one can prove that these are actually 2 distinct factorizations, and you can't, break apart 2 anymore to make it line up with 1 plus square root of 5 of minus 5. Okay, and then let's see, we had the little aside on Fermat's last theorem and where you can actually start to use some of this machinery. Okay, and then we started talking about prime splitting and how we fix it. And so we define this notion of ideal, and this is a tough one because if you haven't already known what an ideal is, it feels pretty rough to have this new notion thrust upon you. But the idea here to keep in your back pocket is it's just like honest to goodness numbers, except better. And every time you're working with an ideal that is principal and generated by one thing, all the things you expect to happen from divisibility in the integers and so forth happen. And it fixes these problems that we noticed earlier. So my plan for today was to dig a little deeper into ideals and this kind of talk through this computation I wrote up yesterday for how ideals end up saving the day. And then I was going to go ahead and do that. Are there any other any questions before we do that about previous things? Any points of confusion or anything like that? All right, cool. So here's the idea. We have these 2 distinct factorizations of 6, and it turns out that we can consider some ideals, P2, this ideal generated by 2 and 1 plus the square root of minus 5. What does it mean to be generated by those 2 things? We just take those 2 things, multiply it by 2 by any integer, that's in there, multiply 1 plus square root of minus 5 by any integer, that's in there, and then we can add them, and we make sure it's an ideal, but it's I guess you could say it's the smallest ideal containing both those elements right there. Okay, cool. And the mantra here for algebraic number theory is to contain is to divide. So we can see that this ideal contains 2 by construction, so it divides 2. So we're thinking of, like, we have this ideal, it's not quite the same as a number because we're not able to generate it with one element, but it kind of behaves like a number in that it divides two. Okay, and so what we end up figuring out is that if I take this ideal right here and square it, I get the ideal generated by 2, the principal ideal 2. So this is kind of like saying that 2 equals this Gothic P2 squared. Likewise, I find that 3 equals the product of these two ideals right here. So when we're taking products of ideals, you can go ahead and take all the products of their generators and see what you get there. And so that's what we've done here. And I guess I should just say I took the products of the generators right here, and then I have all this stuff right here, and I notice all this stuff is divisible by 2, right? So to contain is to divide. So I notice this thing I've just blurred out, this thing I've underlined here is definitely contained in 2 because everything's divisible by 2. But also 6 minus 4 is 2. So 2 is in here as well. If 2 is in here as well, then certainly it contains 2. So to contain is to divide. I got divisibility both ways or containment both ways. And so these things must be equal. So there's some details to work out here, and I kind of wanted to have a little bit for y'all to chew on if you planned on working through this. Likewise, we can do the same thing with 3. As before, all these things are divisible by 3, but 9 minus 6 is equal to 3, so the containment goes both ways. Okay, and then I have these other factorizations here. So 1 plus the square root of minus 5 factors as P2 times P3, and 1 minus the square root of minus 5 factors as P2 times P3 prime. So now if I take everything as ideals, and we like to use this this parentheses notation to indicate I'm talking about an ideal. Sometimes you'll also see 6 OK, for example, right here, which makes sense. It's 6 times every element of OK, and that gives me my ideal. And so once I factor this out as ideals, I have this as the ideal 2 times the ideal 3. Again, with principal ideals, ideal multiplication works how we might naively wish it would work. We can just multiply the generators. So I have this factoring like this. I have 6 equals this product of 2 ideals, and I have these factoring like this, and we see, oh, those are actually the same ideal factorizations. Okay, now I should say here, I think we maybe mentioned this in some of the questions. How do we know we're done? How do we know we factored it into primes? Maybe I just factored it into ideals and it keeps going, and there's some weird ideals with 12 generators I didn't cook up. It's a fact that I can't remember how to prove off the top of my head, but a useful one to know that every ideal, I'm not sure if I can say Dedekind domain, or at least in a ring of integers, is generated by 2 elements. So I might not be principal, but at worst, I'm generated by 2 elements. So that's one of those useful things. Can't remember how to prove it off the top of my head, but it's a good thing to have in the back of your pocket when you're doing some computations with algebraic number theory. Okay, so now I want to figure out, it'd be nice to know, are these things prime? And so one thing I could do is I could say, oh, I could go back to this definition of if a product's in there, is one of the factors of the product going to be in there? My kind of quickly generalized definition of prime. But at least for my mind, it's easier to think about modding out by an ideal and making sure when I mod out by an ideal, I get a domain. So let's see, we could just go ahead and take, if I do z adjoin the square root of minus 5, and I mod out by the ideal 3 and 1 minus the square root of minus 5. Okay, So I'm declaring those things to be equal to 0. So 3 is 0. So all of a sudden I have z mod 3z. And then I have that the square root of minus 5. 1 minus the square root of minus 5 is equal to 0. So the square root of minus 5 is equal to 1. And so that square root of minus 5 just disappears. So I'm just left with z mod 3z. Or it doesn't just disappear. It behaves just like 1. So it doesn't add anything new here. Yeah. Yeah, I should throw an isomorphism in there just to be safe. Yeah, because I guess a priori on z mod 3z, I don't have like something that is, you know, equivalent to square root of minus 5 once I've modded out by 1 minus the square root of minus 5. So, yeah. All right, and z mod 3z is not just a domain, it's a field. So we're super good in that case. So in fact, this ideal is a maximal ideal, and that is a fact about these rings of integers is non-zero prime ideals are actually maximal ideals. So these are not just any commutative rings. They're rather special ones, and we call them Dedekind domains. Okay. So questions about this? Yeah, so the basic idea here is you're working with these things called ideals now because we don't have unique factorization into honest to goodness algebraic integers anymore. But you can do a lot of nice things, you know, modding out by an ideal is not the worst thing in the world, and we can still do some computations. Okay, so I want to make, I think at this point, I'm just going to kind of take it and run with it and try to mention a few theorems that I think are real cool theorems for algebraic number theory, and we'll see kind of see where we get to. It's a crash course, so there's a few theorems I want to mention, so I'm just gonna go for it. And please stop me if you have any questions. There might not be too many full all the rigorous detail proofs. So we had this wonderful thing when we were talking about places with unique factorization called the norm. That helped us show things were prime, and it was a pretty useful tool. So can we recover that? And it turns out you can. And the way we do that is we take our ring of integers and we mod out by our ideal, and then we look at the size of the thing we got. And it turns out we're going to get some finite ring. If it's prime, it's automatically maximal because we're in a Dedekind domain, so we're actually going to get a finite field. And so we can look at how big that thing is. So let's, this is also completely multiplicative. So the product of ideals is the product, the norm of a product of ideals is the product of their norms. So that's really great. We're looking good. And let's see, we want to, I didn't really leave myself enough space here, did I? We want to check and see that this generalizes the norm we're used to talking about, right? So I can take, let's see, z adjoint I, and I can mod out by 3. Okay. And so I get z mod 3z adjoined I. Okay. And now maybe I doesn't actually do anything here. But in fact, we can check that x squared plus 1, that's the polynomial that I satisfies. So maybe another way to think about this right here is z mod 3z adjoined x modulo x squared plus 1. Now, does modding out by x squared plus 1 give me an honest to goodness extension, or does x squared plus 1 actually factor over z mod 3z, and so I'm kind of really getting just 2 copies of z mod 3z crossed, something like that? Well, we can check. It's a quadratic polynomial, so we can just plug in and see if we have any roots. So, 0 squared is 0, 1 squared is 1, and minus 1 squared, I guess I'm saying this is all congruence is mod 3, is what I'm saying here. And minus 1 squared is 1. Actually, it's not even all congruence is mod 3. I didn't even need to use reduction mod 3 there. But that's a set of all representatives in z mod 3z, and we can see none of them square to be minus 1. So this polynomial right here is irreducible. So that gives me an honest to goodness extension of z mod 3z. So, and it's a degree 2 extension. And so what I'm going to get right here, I am so sorry for being so low on space. So what I'm going to get right here is this will be an extension of z mod 3z, a field extension of degree 2. And so this is going to be what we call F9, a finite field with 9 elements. And it's generated as a F3 vector space by 1, or a basis for it as a F3 vector space is 1 and I. In analogy with our number fields, where we have our nice basis as 1 and then powers of our root that we use to create that finite extension of Q, we get a similar kind of story over here. Sweet. So that has 9 elements, has size 9, and then we can take the norm of 3, and this is the norm of norm relative to the Gaussian integers, of course, because 3 can live in a lot of different places and they'll have different norms depending on what number field I'm in. So the norm of 3 here, though, is just 3 squared, right? So sure enough, these things agree. I should probably go ahead and pull up like another page for this, maybe. Let's see. Should we do... Let's see, how about we do a... Maybe we could just check that... Maybe we could kind of... I don't know. How is this? Is this all right, or should we do another example? Right? Okay, cool. So that's the absolute norm, and it's a useful tool for us when talking about ideals. It lets us generalize the norm to talking about ideals. We just mod out by them and see how big the ring we're left with when we mod out by them is. Great. So, if I have, I definitely need to unpack this definition here. I apologize for various reasons. Last night was a bit of a late night, so I'm a little ragged today, but not quite as ragged as my friend Alex. So the next definition we want to make is going to be related to trying to understand how primes in the integers break apart in these number rings. So there's a real nice way of lining this up and understanding it. So I need one more I need one more definition. So, and that's the residue class degree, or residue degree, or inertial degree, or inertia degree. And these terms are confusing, and inertia also means something a little bit different when you start doing. Anyway, I like to call this the residue class degree, and that's what I'll try to call it. And what this is if I have a prime ideal a non-zero prime ideal in OK. And I mod out by it as I told you, as I claimed, prime ideals in these Dedekind domains are actually maximal ideals. And so when I mod out by it, I'm not just going to get a domain, I'm going to get a field. So if this is prime, OK mod P is a field. And in fact, it's a field extension, as we saw in this tiny little scribbled example here. It's a field extension of Z mod PZ for some P. And in fact, there's going to be a unique prime living below down there. So this is going to be a finite field, and it'll be a field extension of Z mod PZ of FP. So I'm going to probably wantonly go back and forth between writing FP and Z mod PZ for these residue fields. Okay, and so we saw this right here with Z adjoined I mod 3, which is a prime ideal in Z adjoined I. I'll write it as 3ZI to make sure we know where our 3 is living here. This is a degree 2 extension of Z mod 3Z. Where now I'm thinking of 3 as the downstairs thing. So this is isomorphic to F9, finite field with 9 elements. This is isomorphic for F3. Okay, and so the inertia degree, the residue class degree, is the degree of this extension. So in this case, it's degree 2. So residue class degree . All right, cool. And I gave myself this, oh, I have a whole new page, cool. So let's find the inertia degree of, and here I used inertia degree when I said I was going to use residue class degree. I normally say residue class degree, and then I was looking up other terminology because I know this is like one of those terms that a bunch of things get tossed around for it, and then inertia degree got stuck in my head. Anyway, so I want to go ahead and try to compute the inertia degree of 7, the prime 7 in the ring of integers of Q adjoined the third root of 2. And so I'm just going to tell you right here, rather than do a bunch of computations, that this ring of integers is just Z adjoin the third root of 2. It's nice. It's monogenic, generated by one element. And we'll hopefully meet an example today of something that isn't monogenic. So when you're first learning algebraic number theory, for sure, all the first examples are like, oh yeah, it's all generated by one element. This is great. This must always happen. It's nice. It's got to always happen. So we'll get disappointed again. First we wanted prime factorization, and then we wanted monogenicity. And we're out on both counts. Anyway, so this is a ring of integers. And I want to find the inertia degree of 7. So yeah, let's see. And maybe a better way to write this ring of integers for now, rather than choosing which root of x cubed minus 2 I'm going to work with, I'll just write it as Z adjoined x modulo x cubed minus 2. Cool. So we just have some x. X is, all I know is x is a root of this polynomial. Awesome. And as before, we're going to go ahead and mod out by 7. Okay. So I take and I mod that out by 7. I'll just put brackets because I don't want to rewrite that, but 7 as an ideal in this ring of integers, not as an ideal in Z. And I see what I get. And so one thing I'm definitely going to get is 7 is now 0, so I'm going to get Z mod 7Z. So got, just write it like this. F7 joined X modulo X cubed minus 2. Okay, so a lot of things can happen here, and it kind of depends on what happens to X cubed minus 2 mod 7, right? How that polynomial behaves. It might not be irreducible anymore, right? It was irreducible over Q for sure, but maybe it's not an irreducible mod 7. Great. So if I have a cubic polynomial and it's reducible, it has a linear factor, right? It has a root. So I can just test and look at all the cubes mod 7 and see if any of them cube to be 2. So, and y'all can see I set myself up with some examples that, yeah. Excellent point. Excellent point. Yeah, so you could look at the Z mod 7Z cross or star, the group of units of that field, right? And if you know that's cyclic, then you know that you can pick a generator that has order 6. Then you cube that puppy, and you know you're going to get how do we want to do that? Well, I'm confusing myself up here. This is how you can tell I'm tired, because I cannot think on my feet. So say what you said again. Mm-hmm. Oh, awesome. Yeah, that's not what I was saying at all. I totally misunderstood you. That's excellent. I like that idea. So you could be naive and do some painful computations, which is what I end up doing a lot. Or you could be clever and say, okay, Fermat's little theorem, which is a real demeaning name for a theorem because it's a pretty great theorem. Says that if I have what is it? A to the 7 minus 1 is congruent to 1 mod 7, which says that for any A in Z mod 7Z, x to the 6 minus 1 is congruent to, well, I guess I don't know why I'm switching to x here. I'll just keep it A. It's congruent to 0 mod 7. And so then I say, okay, that's A to the 3 minus 1, A to the 3 plus 1, congruent to 0 mod 7. And so 7's a field. That's a wonderful thing. Or 7's a field. Z mod 7Z is a field. F7's a field. That's a wonderful thing. And so we don't have 0 divisors. So if I satisfy this, I got to satisfy one of these things, which says when I cube things mod 7, I'm either getting 1 or minus 1, right? Because everything mod 7 satisfies this polynomial. All right. I think I just explained this to myself, and everybody else already knew what was going on. But sound good with this argument here? If I'm cubing stuff, everything mod 7 either satisfies one of these factors, and so it's either got to be 1 or minus 1. So this has no roots. The punchline here is has no roots. Mod 7. Awesome. Okay, so it's a nice irreducible polynomial. So we're taking a field, modding out by an irreducible polynomial. That gives us a degree 3 extension, right? So this puppy right here, this is a degree 3 extension of F7. So by what we know about finite fields, this is going to be F7 cubed. And of course, I have no clue what 7 cubed is, so we're just going to leave it at 7 cubed. And it's actually nicer to leave it like this because we can just see that the residue class degree in this case is 3. So residue class degree 3. All right. And as kind of a byproduct here, what else did we prove about the ideal 7 OK or 7 z adjoin the cube root of 2? I modded out by it and I got F7 cubed. Oh, yeah. Excellent. Right. Awesome. Excellent. Excellent, Ben. So 7 this factors into primes in some way, right? Factors into primes. 7 might not be prime, as we've met many examples. There's plenty of times where you take an integer, look at it over your set of your ring of integers you're working with, and it's no longer prime. But in this case, we modded out by it, and we got a field, so it must be prime. But so it's always true that it factors into primes, right? And in this case, but is a field. So 7 upstairs is prime. And yeah, as Ben mentioned, our word for that is inert. So it took the integral prime 7, raised it upstairs, stayed prime, it's inert. So we say 7 is inert. All right, cool. So as we're going kind of through this, and if you're trying to construct algebraic number theory, you start noticing some patterns with how these factorizations of primes line up. And you probably, if you were developing this field, you'd probably compute hundreds of examples all by hand, by candlelight, as the Black Plague swept through. Actually, I don't think the Black Plague was going around when this was being developed. Anyway, so you compute a ton of examples, and you start to notice some common themes. And so I want to just pull off the covers and tell you kind of what the punchline is here with how we can expect primes to factor. So let's say I have a number field of degree n, and I have p a prime in the integers, and I want to know how p factors in my number field. So I can write it, this is just a generic, this is not this statement right here has no content. It's just saying it has a prime factorization by the fact that, or that we're taking it on faith that rings of integers have unique factorization into prime ideals. So it has some prime ideal factorization. What do I know about that prime ideal factorization? Well, if I take the exponent on each EI, or on each PI in the factorization, and I multiply that by the residue class degree, which we just defined is that degree of the extension of finite fields, and I add all those up, I get the degree of my extension. I get n. So let's see if we can go back and kind of see this a few times in the previous examples we've done. Right here, this has residue cost degree 3, 7 stays prime, so 7 just factors as 7, and that has residue cost degree 3, and that's great because this is a cubic field. Okay, so that lines up with what we hope happens. Here, we had another example of an inert prime. 3 stays prime in Gaussian integers, has residue cost degree 2, and the Gaussian integers are a degree 2 extension of Z. Okay, cool. Let's see. Oh, over here. Okay, so we worked through this example. We found out that 2 factors as the square of a prime. 3 factors as a product of 2 different primes. And over here, well, at least for this example, oh no. At least for this example right here, for this prime, we computed that when I take this ring of integers and mod out by this prime, for example, above 3, I just get Z mod 3Z. So I don't get any residue cost degree extension. Or my residue cost degree is 1. I don't actually get a proper extension of my finite field. And likewise, we can believe the same thing happens if I replace the plus by a minus. So here, 3 factors into 2 primes, and each has residue cost degree 1. And so 1 plus 1 is 2. And this was a degree 2 extension we're working with. That works out. 2 factors into 1 prime. It has exponent 2. The ramification index, we should define that, but this puppy up here is called the ramification index. That's 2. And we can check if we mod out by this thing right here, we'll see that we just get Z mod 2Z. We just get F2. So it doesn't have any, the residue cost degree is 1. There's no non-trivial extension of the residue field. And so this is a 2. And if we multiply that by 1, we get 2, and it's a degree 2 extension. We're happy. Y'all starting to see what we're kind of what's going on here with this summing up to the degree of the number field business? I should, let's see, down here I'll go ahead and say this EI right here, say EI is called the ramification index. And there's been a lot of really good questions about ramification and it being a confusing phenomenon. And so I'll just say that a kind of quick way to define ramification, if we already have this understanding of what's going on, is we would say P is ramified in OK if some EI is greater than 1. So before, when we were first computing examples, I was just like, oh, there's a square of a prime in there, and it's new factorization. And morally that's correct, but this isn't a cleaner way. Yeah. That's an excellent question. And this is one of those things where I'm tired, but I think I can cook up an answer. It might be wrong at first, but we'll get it to be right eventually. So I guess the first thing I'll say is when you have a Galois extension, and if you don't know what Galois means, that's okay. But when you have a Galois extension, the Galois group permutes all the primes above P. And so each EI and FI are actually the same. So in that case, that puts some pretty solid restrictions on which permutations you can use. right? So in a Galois extension, certainly not everything can happen. And I don't think I can say too much more intelligently about a Galois extension with my current level of caffeination. But I can answer your question for an arbitrary extension, and it'll come down to this actual next theorem I want to talk about. And so we can cook up any, you can actually pick your favorite prime and cook up whatever partition you want, and we can like retroactively cook up that as how this prime splits. And it comes down to taking a polynomial in Z mod, pick your favorite prime, let's call it P, in Z mod PZ, you pick a bunch of irreducible factors for your polynomial, pick as many irreducible factors with the appropriate degrees lining up with the FIs you want, raise them each to the EIs you want, multiply them all together. That thing's definitely not, if I just lifted it up to Z adjoined X, it's definitely not irreducible. But I could, like I could multiply all the coefficients by another prime that's congruent to 1 modulo P. That would make it Eisenstein at the other prime, if you know what that means. It would make sure it's irreducible, and whatever prime I have upstairs has the same factorization mod P that I cooked up. And then, my favorite theorem in algebraic number theory says that if you choose appropriately so that you have a prime that doesn't divide this index, which in our example we could do, the factorization of my prime mirrors the factorization of my polynomial mod P. So this is often called Dedekind-Kummer factorization. Ran away there with Kummer. Okay, so yeah, that I have 5 minutes left, and that was a great segue. We're interested in how things factor. Now we have some sort of idea that these summing up all the primes above P with the EIs and FIs is going to give me in. So I have that restriction. But, like if I just give you some degree 7 number field, like how does stuff factor? I mean, I've very clearly padded my examples so they're nice, easy ones to compute with. And so one way, my favorite way to deal with trying to factor primes is with this wonderful theorem right here. So let's unpack this a little bit. I only have 5 minutes, so I'll just try to breeze through it. We'll go with our old friend Q adjoined the cube root of 2. Okay, so that's my number field, and I want to know how primes factor here. There's this really, really, really important hypothesis that if P is a prime that does not divide the index of OK in Z adjoined alpha. So a priori, at first glance, it's not clear that if this is K, it's not clear that OK equals Z adjoined the cube root of 2. I claim that was actually what's going on, and that's the ring of integers, but it might not be. If I have an irreducible polynomial of the correct degree, though, it only fails to be the ring of integers at finitely many primes. There's kind of finitely many primes where it's bad. Those are primes that kind of like divide the discriminant of this polynomial more than the discriminant of the number field. There's just these finite primes that are a problem, as with everything in number theory. Some finite list of primes that are an issue. So if I get away from that finite list of primes, then the factorization of my ideal P is going to mirror the factorization of the polynomial that alpha was a root of, mod P. And we kind of already saw that a little bit with some examples, right? Over here, in this special case, I noticed that when I'm x cubed minus 2, well, I didn't notice it. you notice it. It's irreducible, right? So it doesn't factor at all. It just stays this nice cubic irreducible polynomial. Likewise, 7 stays this nice prime with residue class degree 3. So we can see this pretty directly anytime something's inert, because our polynomial is irreducible and it defines a nice extension of my residue field. But it's a little more subtle in cases where primes are splitting up and you have some ramification and so forth to deal with. So it's a bit trickier to deal with. Keith has some notes where he does this all out. So let's do some other examples here. Oh man, I'm so low on time. Actually, in 2 minutes, I think it's more useful to do a proof sketch, and then maybe I'll post an updated version of these notes with some examples for y'all to do on your own time. So here's why we should even expect this beautiful symmetry between a factorization of a prime and a factorization of a polynomial mod p to line up. So if p doesn't divide this index right here, then OK mod p, OK mod p OK, is in fact going to be isomorphic to z adjoined alpha mod p, z adjoined alpha, right? P doesn't divide this index, so P doesn't know that z adjoined alpha isn't the full ring of integers. As far as P knows, z adjoined alpha is the full ring of integers. You know, it's the other primes where z adjoined alpha is an issue. Okay, so once I have this lined up, we can kind of think of like Chinese remainder theorem, the so-called Chinese remainder theorem, maybe Sun Tzu's theorem. This quotient right here tells us how P factors, right? You know, if I z mod nz, the ring structure of z mod nz tells me how n factors, right? So we can believe this tells us how p factors. Likewise, if I write this right here a little bit differently, and I just write it as z adjoined x modulo f of x and p, the ideal generated by these two things, then I can kind of, rather looking at modding out by f of x first and then p, I'll go ahead and mod out by p first and then f of x. So this is z adjoined z mod pz adjoined x modulo f of x. And in the same vein, we can kind of believe that the ring structure of that tells me how the how f of x factors, right? Okay, well, we had a big chain of isomorphisms here, and on one side we have this tells us how p factors, and on the other side we have this tells us how f of x factors. So those factorizations are going to line up. And I mean, this was a hand-wavy proof sketch. I think Keith does this in about 2 pages, but of course Keith checks all the details and dots the i's and cross the t's, which, as y'all know, is not my strong point. But yeah, this is, I just think that this theorem is particularly lovely, having this nice symmetry between factoring a polynomial mod p and factoring p in the ring of integers you get by adjoining a root of that polynomial. And so I will stop right there and ask for questions.